Welcome back. In today's explainer, we're diving deep into a massive, fundamental shift in energy storage, the sodium-ion battery revolution. Now, right off the bat, I want to make something perfectly clear. We are absolutely not dismissing lithium-ion technology today. Lithium is incredible. It literally powered the modern mobile era. But as we'll see through the engineering and the data we're looking at today, sodium-ion brings an entirely unique utility to the table. It's a technology that is going to profoundly change the world's energy infrastructure.
Look at this number, negative 40 degrees Celsius. I'm hitting you with this right away because, well, if you live in a cold climate, you know exactly what winter does to your electronics and your electric vehicle. Standard LFP, or lithium iron phosphate batteries, seriously struggle in sub-zero temperatures. You can easily lose 30% or more of your usable range if those batteries aren't preconditioned. But sodium ion? It is an absolute game changer for cold climates.
Get this, sodium-ion batteries can retain about 90% of their capacity at negative 40 degrees Celsius. And no, that isn't just theoretical lab data. CATL's newly commercialized Noxtra sodium-ion battery platform proves this capability in the real world. Think about what this breakthrough actually means. It is absolutely crucial for commercial logistics fleets, public transportation systems, and really just everyday drivers in northern climates who need reliable power when the temperature just completely drops off a cliff.
Okay, let's dive into this. Here's our roadmap for today's explainer. We're going to start with the anchor analogy, look into the mass constraint, explore the supply chain economics, and finish up with the grid scale revolution.
Section 1. The anchor analogy. Let's get our baseline comparative framework established.
To really manage our expectations here, we need this central analogy. Think of lithium as a high-performance race car fuel. It's extremely light, it's incredibly powerful, you want it in your cell phone, and you absolutely want it in your luxury long-range EV. Now think of sodium as the reliable, abundant foundation of a city's power grid. It's not built to win a speed race, but it's cheaper, it's safer, and it is everywhere. The big takeaway here is that they are complementary technologies. They aren't fierce competitors trying to destroy one another.
Section 2. The mass constraint. Let's look at the actual physics.
It all comes down to energy density, which is measured in watt-hours per kilogram. This is just the energy-to-weight ratio that determines how much power a battery holds relative to its mass. CATL's commercial Noxtra sodium-ion battery currently sits at around 175 watt-hours per kilogram. Now that is fantastic progress, and the gap is shrinking fast, but premium lithium-ion still pushes well over 200, even up to 300 watt-hours per kilogram. So you're probably wondering, why the gap?
It's simply because of physical size. This is what we call the mass constraint. Lithium ions are tiny, right around 60 picometers in diameter. Sodium ions are much larger and heavier, coming in at 95 picometers. That means they are physically less efficient for high energy density needs. You literally cannot pack as much energy into the exact same physical space when the ions themselves are that much bulkier.
And this brilliantly illustrates how a seemingly little shift on the periodic table forces a massive engineering pivot. Because sodium ions are so large, they physically cannot fit into the standard graphite anodes that we use in everyday lithium-ion batteries. Instead, engineers have to use what are called hard carbon anodes. It's a non-graphitizable carbon structure that essentially has wider gaps to accommodate those bulky, heavy sodium ions. It's a completely different architectural requirement at the microscopic level.
Now, what's really interesting about this benchchem data is seeing the fundamental economic and performance trade-offs side by side. Look at the cost. Sodium ion is hovering around $100 per kilowatt hour compared to lithium's $150. Cycle life? Highly competitive, pushing up to 6,000 cycles. But the real jaw-dropper here is the raw material availability. Sodium makes up roughly 2.3% of the Earth's crust. Lithium? Just 0.006%.
Section 3. Supply chain economics. Let's zoom out from the microscopic level to the global macroeconomic level.
The cost per kilowatt-hour advantage of sodium isn't just because raw salt is cheaper than lithium. It's really about supply chain resilience. Sodium resources are distributed all over the globe. This drastically reduces geopolitical risk and the environmental footprint compared to the highly concentrated, incredibly water-intensive extraction of lithium. In fact, industry estimates show sodium is about 450 times more plentiful globally than lithium. To put that incredible abundance into perspective, consider this specific anecdote from the data. In China's Karhan Salt Lake alone, the sodium reserves are 500 times greater than the entire global lithium reserve combined. Just think about that for a second. One single salt lake holds that much potential. That is the very definition of a truly scalable global resource. And here is the secret economic weapon of sodium-ion, the manufacturing infrastructure. Sodium-ion manufacturing actually shares enough architecture with existing lithium-ion facilities that the transition can happen quickly. We don't have to build an entirely new, multi-trillion-dollar global industry from scratch. We can leverage the factories, the talent, and the assembly lines that are already up and running.
Section 4. The grid-scale revolution. The ultimate endgame for this tech.
Before we talk about the grid itself, we have to understand electrochemical stability. This is a super crucial safety term. It defines the ability of a battery to resist thermal runaway, which is essentially a catastrophic, self-sustaining fire, and operate safely. Sodium is inherently less reactive than lithium. Because of this high electrochemical stability, it's a far safer chemistry to use for massive, stationary installations where you might have literally thousands of battery packs stacked together.
So, the absolutely crucial point is this. For utility-scale energy storage, weight and size matter much, much less than cost and cycle life. You aren't carrying a grid battery in your pocket. Because of that, sodium dominates. It gives us a lower cost per kilowatt hour, it retains its capacity in extreme cold, it boasts high thermal and electrochemical stability, and it relies on an incredibly secure supply chain. Plus, CAT-TL states their sodium-ion energy storage systems can achieve up to 15,000 charge cycles. It's a perfect storm of attributes, making sodium effectively the perfect candidate for storing renewable energy like wind and solar on a massive global scale.
We've covered a whole lot of ground today, from picometers and hard carbon anodes all the way up to global supply chains and massive grid storage, which leaves us with this final thought. As we transition from relying solely on scarce race car fuel to building an abundant global grid, how will a hybrid lithium-sodium future reshape global energy independence? It's a fascinating question, and one that really highlights the brilliant, complementary nature of both of these technologies. Thanks for joining me on this explainer, and keep questioning the science around you.